so if I have, for all x p of x, and let's say p of x is one that we've already looked at, x squared greater than x, the universe of discourse we're looking at is the real numbers, so all the x's are in the real numbers. What this actually means, this is shorthand for writing p of 0 and p of 1 and p of 2 all the way up to p of 100 and so on, and we end it with all the negative numbers and also all the real numbers in between all those. Right? Yes, so that's what for all means. It means no matter what. Now, if you'd like to write out that and, you're welcome to do it, but you'll never ever get done. Right? Because there's an infinite number of real numbers. So that's why we have shorthand for things like this. Okay, so let's find out. Is p of x true for all possible values of x? No, we already figured that out. So if the for all is false, it's super easy to know. So if we find what we call a counterexample, that's one false, right? That's one x that makes p of x false. So whenever you're, speaking English and, someone says, everybody can afford $5 for this, and then you say, well, John can't afford $5 for this, then you've actually found a counterexample, right? And you've just proven that the for all is false. It only takes one counterexample to prove that a for all is false. If you want to prove that it's true, you either can make a truth table that listed all the possible input values, and you show that everything in the truth table is true, right? Except we can't do that with the real numbers, but we could do it with truth tables, right? So actually what we've been doing so far, whenever we prove like an axiom, we're actually showing that for all the values in the world, for our input variables, that a statement is going to be true. So we were doing that. We were proving some for alls. You just didn't know it yet. So how do we know that a for all x, p of x would be true, for example? I'd have to do a mathematical proof that would show me that no matter how I change the values, based on some kind of, math that I'm allowed to do, then I could do it. So what I usually do is I break the world into cases. So for this case, I would break it up into negative numbers, right? Negative numbers are easy, because if you square them, they're always bigger than the original, right? And then 0 breaks it, right? And then all the numbers between 0 and 1 also break it, right? Because if you square a fraction, you get a smaller number. So, but I could prove it's true for x is greater than 1, right? So if I changed my universe to real numbers larger than 1, this could be true all the time. So when I start trying to do the reasoning that would help me prove it, I can actually figure out which part of the universe might actually have this statement be true. And the way I would do it, by the way, for x greater than 1 is I would say we have the statement x squared greater than x. If x is bigger than 1, I can safely divide both sides by x without messing it up, right? So I'm going to divide both sides by x, and I get x greater than 1. Wow. Well, that's awesome. So this actually, for all x greater than 1, p of x is actually true. And I just proved it because basically I took my x's and multiplied both sides by x, and then I get x squared is greater than x. So that's like what we'd have to do. We'd have to do a mathematical proof with some legal math to show that it was always true. Are we going to do that very much? No. We're going to look at, for a little while, we're just going to look at predicates and see how often they're true. We're not going to make you do huge proofs of them. We're just going to try to figure out how to translate some English into predicate calculus and also figure out how we can combine predicate calculus statements. Okay, so just to recap what we've done so far,